Okay, hello. Welcome to some practice problems with simple harmonic motion. So exciting. Okay, let's go ahead and jump right in. As always, if you have questions, go ahead and leave them in the Q&A area, question and answer area. Okay, so this first question is actually an experimental design question, which technically is not going to be on the exam this year, but always good to do because the second half of this problem actually has some really great quantitative, qualitative translation stuff. So we have a physics lab group of students are provided with a sphere of unknown mass, a roll of string, a ring stand, and measuring devices that are commonly found in physics labs. The students must graphically determine the acceleration due to gravity near the Earth's surface by putting the sphere into simple harmonic motion. So the fact that they mention simple harmonic motion means we're probably going to be dealing with probably one of two equations. So the first is the position versus time equation, which is x equals a, where a is the amplitude, cosine 2 pi, frequency times time, or the period of a pendulum equation, t equals 2 pi square root L over g, where L is length and g is acceleration due to gravity. On the reference table, there are two period equations. So the one with the pendulum is labeled as TP. Okay. We also might get into some conservation of energy stuff, maybe some force stuff. So we need to state a basic physics principle, law, or equation that a student could use to graphically determine the acceleration due to gravity near the Earth's surface by putting the sphere into simple harmonic motion. Now, because they explicitly mention simple harmonic motion, we're probably going to want to use one of these two equations. If they had said, using energy conservation, how could they find the period of the pendulum? Then we might, obviously look at energy. But because they say simple harmonic motion, we want to focus in on those simple harmonic motion equations. So the one that we're going to use between these two is the only one that has g, or acceleration due to gravity, in it, and that's the period of a pendulum equation. So the 2 pi square root L over g. So again, g is what we are looking for. Period, remember, is the time to complete one rotation or revolution, and L is the length. So period and length are easy enough things for us to measure in a physics lab with pretty basic equipment. Okay, so using this equation, we can help, or using the equation, that can help us set up this table down here, which is where we need to experimentally design the experiment. Duh. So in the table, we're going to list some quantities and associated symbols that would be measured in the experiment and the equipment you would use to measure each quantity. You don't have to fill in any rows. If you need additional rows, they're there. So like I said, we're looking for G, which means the two things we're going to measure is period and length. So quantity to be measured, period. Its symbol is T, and we use stopwatches to measure period. Okay. And then we also need length, which we measure with a symbol L, and we measure that with a meter stick. I usually write my L's when I'm writing stuff out in cursive, like my lowercase L's, because sometimes I don't know if that's a 1 or an L or an uppercase I. So that's why I always write my L's in cursive when I'm doing L as a little variable. Okay. So then we need to describe an overall procedure. Okay, so first things first, we need to set up the pendulum. And it'd be great if I could spell pendulum. My spelling has gotten worse in quarantine, guys. Now you might be thinking, do we need to find the mass of the pendulum? Well, mass isn't in this equation that I talked about, so no, we actually don't need to find the mass of the pendulum. Okay, so we're going to set up the pendulum. We're going to set the length to, let's say, 10 centimeters. We're going to displace the pendulum by a small angle. We want to keep it small. Okay, and now you might be thinking, well, does the angle matter? Well, angle or initial displacement is not in the equation, so no. This displacement angle could also be considered the amplitude. So we're going to displace the pendulum by a small angle and measure the time to complete 10 periods. Divide by 10 to find t. Okay, so remember we kind of talked about this in class, how we don't measure the time it takes for one because there's a lot of human error. So instead we usually measure the time it takes to complete 10 periods and then divide by 10. Okay, so we do that. Then of course we want to reduce experimental uncertainty. So we're going to repeat 1 through 3 and find the average of, let's say, 3 periods. And then we're going to repeat 1 through 4 for, let's say, 5 additional. No, let's say I'm going to do a total of 7. I like 7. It's my favorite number. 6 additional lengths. Okay, so that's some ways we're going to do experimental uncertainty. We can't just do one length because that wouldn't make a very good graph. We'd have 1 point on our graph. Okay, and by doing multiple trials and finding the average, that's how we're getting rid of experimental uncertainty. Okay, so I'm just going to check for questions real quick, and it doesn't look like there are any. Okay, so now on to the next part. Okay, so we have in a second experiment, the students attach the sphere to a string. Right, that's I'm just checking and making sure that, yeah, that's all we needed. Okay, so in a second experiment, the students attach a sphere to a string and undergo simple harmonic motion between x, y, and z. Point X and Z are maximum displacement from equilibrium, and point Y is at the sphere's equilibrium position. As the sphere swings along its arc, the student cuts the string at point Z. Okay, so predict the motion of the sphere after the string is cut in terms of the sphere's displacement, initial speed, and acceleration. Okay, so let's think about this. Okay, so at this location here, at Z, right? Remember, we are momentarily at rest. Okay, so we have no velocity in any direction because we are momentarily at rest. So I'm going to talk about that. So at Z, the sphere is momentarily at rest. Okay. So I talked about initial speed. Now I need to talk about acceleration. Okay, so if the string, or let's talk about when the string is there. So I have an FG and I have a force of tension. Well, if the string is cut, then the force of tension goes away, and the only force acting on the object is the force of gravity, which means the force of gravity is the net force, so our acceleration is going to be the acceleration due to gravity. So at Z, if the string is cut, the only force acting on the ball is 0. Or not is 0. Wow, nope. The only force acting on the ball is gravity. So the acceleration of the ball is the acceleration due to gravity. So now we need to talk about what actually happens to the ball. So if we have an initial speed of 0 and the only force acting on us is a downward force of gravity, then we're just going to fall straight down. So therefore, the ball will fall straight down. Okay. Now, if the ball was at any other location other than Z or X, the ball would have some initial X direction velocity and some Y direction velocity. So let's say we release the ball right here. Let's call this position M. Well, and we're moving that way. Well, at this no, let's actually move up. We're swinging up towards Z. So if we're swinging up towards Z, ball M has some initial Y, upwards Y velocity and rightwards X velocity. So if I release it at position M, the ball would rise up a little and then fall down like a projectile. But because I'm releasing at Z, we have no initial velocity because the velocity at Z is 0. Therefore, we're just going to fall straight down, which is a weird thing to think about, but that's what occurs. Okay. All right. So now we went from D to C. That's good. So now the student must graph the data so they can determine the acceleration due to gravity near the Earth's surface. So I think this somehow got out of order, and I have a feeling we were supposed to do C after we talked about the experimental part. So that's cool. All right, so remember in the experiment, we're basing it all off of this equation, right? And we're measuring period and length. So the first thing we need to do is indicate which quantities could be graphed on the horizontal and vertical axis to determine the acceleration due to gravity by using a best fit line. So we definitely need a line. You may use the remaining columns in the table as needed to record any quantities, including units that are not already in the table. Okay, I don't think we need to do that. So I'm going to rearrange this equation for G, since something about that best fit line is going to need to give me G. So I'm going to divide both sides by 2 pi firstly. Square root L over G, and then I'm going to square both sides. So I have period squared over 4 pi squared equals L over G. And I'm going to divide both sides by, actually, you know what? No, I'm not going to do that. I'm going to multiply. Nope, I'm going to cross multiply. There we go. So TP squared G is L 4 pi squared. I'm going to divide by TP squared. Toilet paper squared. So G is 4 pi squared L over TP squared. Okay, so since this is a division that I'm saying between L and TP, that's a good idea that I'm going to need to use a slope. So the top of that fraction tells me what should be graphed on the y-axis. The bottom tells me what should be graphed on the x, and slopes are change in y over change in x. So on the vertical axis, I want to graph 4 pi squared L. On the horizontal axis, I want to graph TP squared. Okay. So this vertical axis would have units of meters, since 4 and pi don't have units. And this horizontal axis would have units of seconds squared. So the students determine that the slope of the line is m, derive an equation that can be used to determine the acceleration of gravity. Using the slope of the graph that's described by the quantities plotted from C, express your answer in terms of the slope m. Oh, okay, so I already did that. So m is G is 4 pi squared over L over TP squared. Easy enough. Okay, so let's go ahead and check my points. So in part A, which is where I needed to figure out what physics thing to use, I get 1 point for the period of a pendulum equation. Hooray! Then part B was where I get into actually doing the experiment. So I get 1 point for listing relevant and appropriate equipment that matches the measuring quantities. I did that. We need to measure the length and the period for stating that the length of the string should be changed. I get a point for stating multiple trials should be conducted for each length. And I get 1 point for stating that the sphere should be only released from small angles. So I did say small angles. Wonderful. Hooray, I got all the points. Okay, now C was the one I just did, even though D came before C. So C was the graph. So I get 1 point for choosing two quantities that, when graphed together, can be used to determine the acceleration due to gravity. So I said for pi squared L versus TP squared. So let's see if that's an answer. It is right here. Hooray! Okay, so I get that point, and then I get a point that the slope, oh, it looks like they forgot to. So 1 point is earned for correctly relating the slope of the equation to the graph. I did that. So this example is not what I did, which is why it looks wrong. And then 1 point for correctly solving for the acceleration due to gravity, which I did. Hooray. I did it all. Okay, and then part D. Let's see if this. So I get 1 point for stating the displacement of the sphere will be vertically downwards. I did that. And 1 point for stating that the sphere has an initial speed of 0 but accelerates at g. I did that. So again, remember that was that weird part where we had the sphere at x, y, and z, and we had to figure out where the sphere was going to go. Okay, and because we were at z and our initial velocity was 0, we just dropped straight down. Okay, anywhere else, the sphere would turn into a projectile. Okay. Any questions? It does not look like we have any questions. Awesome. So we're going to go ahead and head to the next one, which is a spring problem. Okay. Boop. Sorry, I'm just switching between windows here. All right. So again, the next one is a spring system. Okay. So we have a block of mass M on a horizontal surface attached to a horizontal spring of negligible mass. The other end of the spring is attached to the wall. There's negligible friction. The center of mass of the block is stretched a horizontal distance of 0.25 beyond its equilibrium and release, so it undergoes simple harmonic motion. A graph of the spring potential energy of the system, block spring system as a function of horizontal position, is shown. Okay. So remember, spring potential energy is 1/2 kx squared, and this horizontal position is x, which is why we see this nice parabolic shape. Okay. So what we're essentially viewing a graph of is a situation like this, where a block is displaced. This is negative 0.25. This would be positive 0.25. There's a 0 there. And it oscillates back and forth. So some equations we might need is the position equation for simple harmonic motion, the period of a spring system, which is the 2 pi square root of m over k. Because we're also dealing with springs, we might need the force that acts on a spring. So force is kx. And then we already have the spring potential energy equation. And remember that spring potential energy converts back and forth to kinetic energy in this sense. So the first thing we need to do is sketch the graph of the force exerted by the spring on the block as a function of the block's horizontal position. Okay, so we need to figure out what direction or when is the force going to be positive, when is the force going to be negative. Okay, so in general, the positive direction is considered to be rightward. Okay, and this force always points toward equilibrium. Okay, so if we are to the left of equilibrium, the spring force always points right. If we are to the right of equilibrium, the spring force always points left, which means from negative 0.25 to 0, we need to have a positive force, and from 0 to 0.25, we need to have a negative force. Okay. Now the graph is asking us to graph force versus x. According to this equation, that's a direct relationship, which means I should see a line graph between those two. Okay. So here's 0.25. And here's 0.25. So I need a line graph that goes through 0 at 0, whoop, and goes like that, okay? Because whenever I'm to the left of equilibrium, my force is going to be pointing to the right. Whenever I'm to the right of equilibrium, my force is to the left. When x is 0, F is going to be 0 because Fs is Kx. And remember, it's a line graph because F and X have a direct relationship. Okay, so the next thing we need to do is calculate the period of oscillation for the spring system. So I need to use the equation 2 pi square root of m over k. All right, so let's see what information I'm given up here. Well, I have the mass of the block, that's good. But looking through this, it looks like I'm not given the spring constant. Okay. Now, if this graph down here actually had numbers, I could actually use the slope of this graph to find the spring constant. Because if I do Fs over x, I get k. Just change in y over change in x. But my y-axis doesn't have numbers, so I can't use this graph. So maybe I can use the spring potential energy graph because spring potential energy has that k value in it as well. Okay, so I see that at a position of 0.25, the spring potential energy is 10 joules. So I can use the equation for spring potential energy to help me find k. So 10 joules is 1.5 k, 0.25 meters squared. Okay, so I'm going to multiply both sides by 2, and that gives me 20. So let's see here. So I have 10 times 2 is 20, and then I'm going to divide by 0.25 squared, gives me 320 newtons. Remember, the units is newtons per meter because it's a measure of the amount of force needed to stretch the spring. So now that I have k, I can find the period. So 2 pi square root 0.4 kilograms. I think that was the mass. Yep. Over 320 newtons per meter. All right. So we got to do the square root. Nope, 0.4 divided by 320. We're going to square root that. Then times 2 times pi. I get a period of 0.22 seconds. Okay. Now that kind of like straight out math, not going to be on this year's AP exam, unfortunately. Or fortunately, I don't know, maybe. It definitely will be a lot of writing. Just a lot of writing, not a lot of math. Okay. So a new block of mass 1 kilogram is attached to the spring. The center of mass of the block is stretched to a horizontal distance of 0.25 meters. So same spring, but different mass. And released from rest such that the block spring system undergoes simple harmonic motion. The grid below represents the kinetic energy of this new block spring system as a function of the horizontal position of the mass. Sketch a curve for the kinetic energy of the block spring system as a function of the horizontal position. Okay, so let's think if the maximum amount of energy is going to change. So in this system, the maximum amount of energy is set by that initial potential energy. Since x and k are still the same, that means I still am going to reach a maximum energy of 10 joules. Okay, so that maximum kinetic energy of 10 joules is going to happen right at 0. Okay. At the amplitudes of 0.25, remember the object is momentarily at rest. So that means there is 0 kinetic energy. And from there, we're just going to kind of follow an inverted shape of the potential energy graph. So kind of an upside down U. So if I was to graph the potential energy on top of it, it would look something like this. right? Where they're kind of inverses or opposites of each other. Okay, but the amount of energy in this system doesn't change. What is going to change is how fast the object moves, because we're changing the mass. Okay. All right, and that actually ends up being the end of this problem. So let's see what my points are. So this part A was for the graph. So I get 1 point for a straight line that passes through the origin, and I get 1 point for a curve or line with a slope. Hooray. So because my graph was through the origin and had a negative slope, I get all of those points. All right. Now for the next part, we were looking for the period of the pendulum. So the first thing we needed to do is find the spring constant, which I did correctly. Okay, and that actually got me 2 whole points. Okay. And then I needed to find the period using the period equation, and that got me my last of the 3 points for this problem. Now part C was the graph, I'm pretty sure. So we get 1 point for a minimum value at negative 0.25 and 0.25, which I did. It was 0, and a value of 10 at 0 meters. So, and then the last point is earned for the shape. So I get a concave down parabola, and this is essentially what I drew. So you could lose that last point if you drew straight lines instead of a parabola. Right? And that is the end of this problem. And it looks like there are not any questions. So we are going to say that this is the end of this practice problem session. I will see you guys soon. Tomorrow, we're not going to do any practice problems. I'm just going to kind of host live office hours starting at 1, and I'll stay on until probably 2:30. That way you guys can just pop in and out with questions that you might need me to go over. So I will see you guys tomorrow. Bye.